Have you ever just stopped and wondered how the code an engineer writes actually becomes that tiny, intricate city inside a computer chip? Well, today we're pulling back the curtain on a super critical step in that whole process. It's a kind of digital magic, really, that turns an abstract idea into a concrete plan for manufacturing. I mean, that's a huge question, right? But it's the fundamental one behind every single piece of tech we use. From the smartphone in your pocket to the massive servers that run the internet, it all starts with this incredible journey from a simple concept to a piece of silicon. You can kind of think of building a chip like building a skyscraper. It doesn't just appear out of nowhere. The entire process, from that first little spark of an idea to a finished working product, is really broken down into three major stages. So, first up, you've got system design. That's the architect's high-level vision. Then you get to the RTL to GDS flow, which is basically a fancy way of saying we're turning code into a final layout. And this is where the vision becomes a super detailed blueprint. And finally, there's fabrication, where the construction crew comes in and actually builds the thing. We're going to focus right smack in the middle on that absolutely crucial blueprinting stage. Now, inside that blueprinting stage, the very first, and you could argue one of the most important steps, is something called logic synthesis. You should think of it as the master translator, or maybe an automated general contractor. Its whole job is to take the architect's plan and create a precise, buildable instruction manual from it. So what is it exactly? Well, think of it this way. Logic synthesis is this automated process that takes a high-level description of what a chip is supposed to do, and it turns it into a detailed circuit diagram of how to build it, using a very specific set of pre-designed parts called logic gates. It's the essential bridge between the world of programming and the world of physical electronics. And this slide just brilliantly illustrates that core transformation. Over on the left, we've got the input, which is called RTL, or Registered Transfer Level Code. It describes the design's function, what it's supposed to do, how data is supposed to move around. Then, on the right, you get the output, the net list. This is the explicit construction plan. It's a list of specific logic gates and exactly how they're all wired together to make that function happen. Okay, so this digital translator can't just work in a vacuum, right? To do its job correctly, it needs a recipe. And that recipe has three absolutely essential ingredients. If you get any of them wrong, the final chip just isn't going to work the way you want it to. Ingredient number one is the design itself, the RTL code. This is the source of truth, written in a language like Verilog. It doesn't just describe the chip, it really captures its very soul, all the logic, all the behavior that's going to make it tick. The second ingredient is the technology library. You can think of this file as a parts catalog for the synthesis tool. It lists every single available component, every AND gate, every NOT gate, you name it, along with all their specific characteristics, like their size and how fast they are. The tool can't use a single thing that isn't in this catalog. And finally, we have the constraints. This is basically the client's list of demands. It defines the goals for the project. How fast does this chip need to be? That's performance. How much battery is it allowed to drain? That's power. And how much physical space can it actually take up on the silicon? That's area. But here's the thing. Just translating the code into a bunch of gates, that isn't the really hard part. The true genius of logic synthesis is how it solves this incredibly complex optimization puzzle, using those constraints as its guide. You know, the source material just hits the nail on the head here. It says the central challenge is the optimization. The tool has to take the design, that library of parts, and all those constraints, and then figure out the absolute best possible combination of gates to meet all the goals. And this brings us to the really crucial point. It's a constant balancing act between three competing goals: performance, power, and area, or PPA as we call it. If you tell the tool, make this chip faster, it'll likely pick bigger, more powerful gates. But guess what? That increases both the area and the power consumption. If you say, nope, prioritize saving power, it might use smaller, slower gates, and that's going to hurt performance. The synthesis tool is constantly making millions of these tiny trade-offs to find the best possible solution. It's amazing. So how does it actually pull off this incredible balancing act? Let's take a quick peek under the hood at the four main steps the synthesis engine takes to transform that code into an optimized blueprint. So it basically happens in four main phases. First, there's a basic translation of the RTL code into a generic circuit. Think of it like a rough first draft. Second, it does logic optimization, simplifying that circuit as much as it possibly can, kind of like a mathematician simplifying a crazy complex equation to make it more elegant and efficient. Third, and this part is critical, is technology mapping. This is where the tool swaps out all those generic gates for real physical parts from that library catalog we talked about. This is where the design meets reality. And finally, it does one last round of technology-dependent optimization, fine-tuning everything based on the specific properties of those real parts to squeeze out every last drop of performance and hit those PPA targets.
And after all that translation, all that balancing, and all that optimization, we finally arrive at the final output. The digital blueprint is complete, and it's ready for the next team in the assembly line.
The final product is what we call the gate-level netlist. This thing is the master document. It's the fully optimized construction plan that details every single component and every single wire. It gets handed off to the physical design engineers, who then get the fun job of figuring out how to actually lay all this stuff out on a tiny piece of silicon. So the next time you pick up your phone or fire up your computer, you can appreciate this invisible, automated genius that's working behind the scenes. It's the process that builds the digital brains of our entire world. And it leaves us with a really fascinating question. As our chips become exponentially more powerful and complex, how are these synthesis tools, these amazing digital translators, going to have to evolve just to keep pace with our own imagination?